So in last lecture we have studied the momentum of inertia of a spherical shell about its diameter. Now in this lecture we are going to see the momentum of inertia of a solid cylinder about its axis of symmetry and the axis perpendicular to its axis of the symmetry. Now let us suppose this is a solid cylinder and this is called as the axis of the symmetry of the cylinder. Now let m be the mass of the cylinder, r be the radius of the cylinder. So this distance is r, which is the radius of the cylinder, and let l be the length of the cylinder. Now pi r square l is the volume of the cylinder, of this whole cylinder, pi r square l. And now if I consider some small coaxial cylinders of the width dx, let me show it here. So this is width dx of the small cylinder which is inside the solid cylinder. This is imaginary but obvious. So this width is dx, and let the distance of this coaxial cylinder from the axis of symmetry be x. Okay, now this is called as a axis of the symmetry, and about the axis of the symmetry the cylinder is rotating, and we have considered a small coaxial cylinder inside this solid cylinder having width dx and which is at a distance of x from the axis of the rotation. Now the volume of this coaxial cylinder will be, this will be 2 pi r in, not r, 2 pi x into l into dx be the volume of the coaxial cylinder, 2 pi xl into dx. Now mass per unit volume of this total cylinder will be m upon pi r square l, and this mass per unit volume multiplied by the volume of the coaxial cylinder will give us mass of the coaxial cylinder. So let me multiply it, 2 pi xl dx. So this is a mass per unit volume of this total cylinder and multiplied by the volume of coaxial cylinder. So that is going to give me the mass of the coaxial cylinder which we have considered as a dm. Okay, now I can write this dm is equal to, so this l will get cancelled, then this pi will get cancelled, and what we have left with is a 2m upon r square x dx. Now if I want to calculate the momentum of inertia of this coaxial cylinder about the axis of the rotation, which is axis of the symmetry of the cylinder, and let us call it as x dash. So momentum of inertia of this coaxial cylinder, consider it as a IC coaxial cylinder. So it will be, so this mass of the coaxial cylinder multiplied by the distance, the square of the distance from the axis of the rotation, which is x square. This is the axis of the rotation and the distance from the axis of the rotation will be x. Okay, and this is the definition of the momentum of inertia, mass multiplied by the square of the distance from the axis of the rotation. So this will be the momentum of inertia of this coaxial. So the momentum of inertia of all such a small coaxial cylinders, then I am going to get the momentum of inertia of the solid cylinder about this x dash. Now if I integrate, so this will give me the total integration. So I see, and this running from 0 to r, so I can write it as integration 0 to r. So this dm is nothing but 2m upon r square x into this x square into dx. So 2m upon r square, these terms are constant, and what we are left with is x cube dx from 0 to r. And if I solve this, 2m upon r square into r raised to 4 upon 4, which is nothing but m r square upon 2, or generally we write it as a 1/2 m r square. So this is the momentum of inertia of a solid cylinder about the axis of the symmetry. This I is equal to 1/2 m r square. Now let us see what is the momentum of inertia of the solid cylinder about the axis perpendicular to the axis of the cylinder. Axis of the symmetry. Now this is a solid cylinder, and this is the axis of the symmetry, and now we have to find the momentum of inertia about the axis perpendicular to the axis of the symmetry. Now this is the axis perpendicular to the axis of the symmetry. Let us call this as a y dash. Now we have to consider the small coaxial rings of width dx and having distance x from the axis of the rotation. Now m be the mass, r be the radius, and l be the length of the solid cylinder. Now if this is the case, then m upon l into dx, this will be the mass of this small disk. The momentum of inertia of this disk about its diameter is given by m upon l dx into r square upon 4. This derivation we haven't calculated. Okay, we have directly taken this formula, plus m upon l into dx into this x square. So this is nothing but the momentum of inertia of this small disk about the axis perpendicular to the axis of the symmetry. So let us call this as a I d. This I is nothing but integration from l minus l by 2 to plus l by 2. So this whole term m upon l dx r square upon 4 plus m upon l dx into x square. So let me take common m upon l. So from minus l by 2 to plus l by 2, the remaining terms are r square upon 4 plus x square. So it will give me m upon l r square x upon 4 plus x cube from minus l by 2 to plus l by 2. And if we solve this, you are going to get, so this r square upon 4, l will get cancelled, and l cube upon this l, it will be l square upon this 12. This is the momentum of inertia of this whole solid cylinder about the axis perpendicular to the axis of the symmetry. Now if this r is very small as compared to the length, for example, if you are considering any long wire is also cylindrical, but its radius is very small as compared to its length. So for such wire, so this r can be written as ml square by 12, but obvious m will be there outside of this. So for a wire, so the momentum of inertia will be ml square by 12, and this is the momentum of inertia of the solid cylinder about the axis perpendicular to the axis of the symmetry. So consider this as equation 1, this as equation 2, and this as equation 3. From equation 1, 2 and 3, we can say that this momentum of inertia is strongly dependent on the shape of the body, and also it depends on the axis of the rotation of the body.